YAML. sklearnutilsparallelParallel. Description: the parallel class in scikit-learn's parallel module provides a convenient way to parallelize computationally intensive tasks within your machine learning workflows. It allows you to distribute the workload across multiple CPU cores, or even utilize multiple machines for faster processing. This is especially beneficial for tasks like model training, cross-validation, or feature engineering, where significant computational resources can be leveraged to expedite the process. Inputs. N jobs. This parameter specifies the number of jobs to run in parallel. A value of -1 indicates that all available processes will be utilized, while a positive integer specifies the number of cores to use. Verbose controls the verbosity of the output. Setting it to 0 disables all output, while higher values increase the level of detail displayed. Backend determines the backend used for parallel execution. Options include low-key, threading, and multiprocessing, each with its own strengths and weaknesses. Prefer indicates the preferred execution method. Options include processes and threads, influencing the choice between multiprocessing and threading for the backend. Timeout sets a maximum time in seconds to wait for a job to complete. If a job exceeds the timeout, an exception is raised. Outputs. Results: a list containing the results of each task executed in parallel. Steps. The parallel class accepts a function func and a sequence of input data iterable as input. It divides the input data into chunks and assigns each chunk to a separate worker process or thread, depending on the chosen backend. The worker processes or threads execute the specified function on their assigned chunks. Upon completion, the results from all workers are gathered and returned in a list. Metrics. Execution time: the total time taken to complete the parallel execution. Speed up: the ratio of the sequential execution time to the parallel execution time. Resource utilization measures how efficiently CPU cores or other resources are being used during parallel execution. Visualization plots. Task execution timeline: a visual representation of the start and end times for each task, illustrating the overall parallel execution process. Resource utilization plot: a graph showing the percentage of CPU usage or memory consumption over time during parallel execution. Fine-tune parameters. N jobs experiment with different values to find the optimal number of cores to utilize, considering the available hardware resources and the computational intensity of the task. Backend: select the most suitable backend based on the type of task and the specific requirements of your application. Prefer influence the backend choice by prioritizing processes or threads for better efficiency based on the task's characteristics. Timeout: adjust the timeout value appropriately to prevent tasks from running indefinitely and causing delays. Uncertainty methods. Now, challenges and fixes. Challenge 1: excessive memory consumption when processing large datasets. Parallel execution can lead to high memory usage, potentially causing memory errors or system instability. Sample use case that resulted in challenge 1: parallel processing of images with complex feature extraction methods. Fixes to challenge 1: reduce the batch size of the data being processed. Use a more efficient data representation or compression technique. Utilize a backend that supports shared memory, like low-key, to reduce memory overhead. Challenge 2: communication overhead. The communication between worker processes or threads can introduce overhead, particularly for tasks with small amounts of computation per data point. Sample use case that resulted in challenge 2: parallelizing a simple function that performs minor data transformations. Fixes to challenge 2: Increase the batch size of the data being processed to reduce the relative overhead of communication. Use a backend that minimizes communication overhead, like threading for tasks that are CPU bound. Optimize the data serialization and deserialization processes used for communication between workers. Challenge 3 serialization issues. Certain data types or objects may not be serializable, preventing them from being transferred between processes or threads. Sample use case that resulted in challenge 3: parallelizing a function that utilizes custom objects that are not pickable. Fixes to challenge 3: ensure that all data types used in the parallel function are serializable. Implement custom serialization and deserialization methods for non-pickable objects. Consider alternative data structures or libraries that provide better support for serialization. Challenge 4: synchronization errors when multiple processes or threads access shared resources. Synchronization issues can arise, leading to data corruption or unexpected behavior. Sample use case that resulted in challenge 4: parallel updates to a global dictionary or file. Fixes to challenge 4: utilize locks or other synchronization mechanisms to ensure exclusive access to shared resources. Implement thread-safe data structures or libraries for managing shared resources. Carefully consider the implications of parallel access to shared resources and ensure proper synchronization is implemented.